Hey guys, welcome back to another episode of my channel. My name is Keika. I'll be going over Campbell's biology textbook, chapter by chapter, section by section. This video will be going over concept 4.3. A few chemical groups are key to molecular function. So, the distinctive properties of an organic molecule depend not only on the arrangement of its mostly carbon skeleton, but also on the various chemical groups attached to that skeleton. These groups may participate in chemical reactions or may contribute to function indirectly by their effects on molecular shape. They help give each molecule its unique properties. So I wrote, distinctive properties of an organic molecule relies on both the arrangement of the carbon skeleton and the chemical groups attached to that skeleton. Chemical groups may go through chemical reactions or contribute to function indirectly by their molecular shape. The chemical groups most important in the processes of life. Consider the differences between estradiol and testosterone. These compounds are female and male sex hormones, respectively, in humans and other vertebrates. Both are steroids, organic molecules with a common carbon skeleton in the form of 4 fused rings. They differ only in the chemical groups attached to the rings, shown here in abbreviated form, where each corner represents a carbon and its attached hydrogens. The distinctions in molecular architecture are shaded in blue. So here we see estradiol and testosterone. So here, like, the shape itself looks the same, but here we have a carbon H3 and an oxygen double bonded here, whereas estradiol only has a HO group here. Okay. The different actions of these two molecules on many targets throughout the body are the basis of sexual characteristics, producing the contrasting features of male and female vertebrates. In this case, the chemical groups are important because they affect molecular shape, contributing to function. In other cases, chemical groups are directly involved in chemical reactions. Such groups are known as functional groups. Each has certain properties, such as shape and charge, that cause it to participate in chemical reactions in a characteristic way. The 7 chemical groups most important in biological processes are the hydroxyl group, carbonyl group, carboxyl group, amino group, sulfhydryl group, phosphate group, and methyl group. The first 6 groups can be chemically reactive. Of these 6, all except for sulfhydryl group are also hydrophilic, and thus increase the solubility of organic compounds in water. The methyl group is not reactive, but instead often serves as a recognizable tag on biological molecules. Study figure 4.9 to become familiar with these biologically important chemical groups. Note in the examples column of the figure that the carboxyl group and the amino group are ionized at a normal cellular pH. So this is figure 4.9. Here we see the groups that they mentioned earlier. We have the hydroxyl group, OH, carbonyl group, carbon double bonded to oxygen, carboxyl group, carbon, oxygen, and hydroxide, I believe, NH2 for the amino group, sulfhydryl group, SH, phosphate group, OPO32, and methyl group, CH3. So these are the different chemical groups that are important in the process of life. And I'm gonna go over my notes. Estradiol and testosterone. Both are sex hormones that are steroids, organic molecules with a common carbon skeleton in the form of 4 fused rings. Difference only in the chemical groups attached to the rings. Results are the basis of sexual characteristics. So just to add, it just shows that the chemical groups attached to the rings result in the difference between male and female characteristics. So if the chemical groups were the same, then we wouldn't have those differences between male and female. So it just shows that like the structure of the molecule is very important. Chemical groups are important because they affect molecular shape, contributing to function. Functional groups are chemical groups that are directly involved in chemical reactions. There are 7. Hydroxyl, carbonyl, carboxyl, amino group, sulfhydryl, phosphate, and methyl. The first 6 here are chemically reactive, and only sulfhydryl is hydrophobic. The rest are hydrophilic. Okay. ATP, an important source of energy for cellular processes. The phosphate group, Bro, in figure 4.9 shows a simple example of an organic phosphate molecule. A more complicated organic phosphate, adenosine triphosphate, or ATP, is worth mentioning here because its function in the cell is so important. ATP consists of an organic molecule called adenosine attached to a string of 3 phosphate groups. So here we have ATP, where 3 phosphates are present in series. As in ATP, 1 phosphate may be split off as a result of a reaction with water. This organic phosphate ion, HOPO3 2 negative, is often abbreviated in this book as P. This little P here is often abbreviated this way in this book. And a phosphate group in an organic molecule is often written as this P in a circle. Having lost 1 phosphate, ATP becomes adenosine diphosphate, or ADP. Although ATP is sometimes said to store energy, it is more accurate to think of it as storing the potential to react with water or other molecules. Overall, the process releases energy that can be used by the cell. You'll learn more about this in concept 8.3. So, ATP, or adenosine triphosphate, consists of an organic molecule adenosine attached to a string of 3 phosphate groups. 1 phosphate may be split off as a reaction with water, and it results in losing an organic phosphate ion. ATP then becomes adenosine diphosphate, ADP. ATP stores the potential to react with water or other molecules, thus releasing energy that can be used by the cell. The chemical elements of life, a review. Living matter, as you have learned, consists mainly of carbon, oxygen, hydrogen, and nitrogen, with smaller amounts of sulfur and phosphorus. These elements all form strong covalent bonds, an essential characteristic in the architecture of complex organic molecules. Of all these elements, carbon is a virtuoso of the covalent bond. The versatility of carbon makes possible the great diversity of organic molecules, each with particular properties that emerge from the unique arrangement of its mostly carbon skeleton and the chemical groups attached to that skeleton. This variation at the molecular level provides the foundation for the rich biological diversity found on our planet. So, the chemical elements of life, a review. Living matter consists mainly of carbon, oxygen, hydrogen, and nitrogen, with smaller amounts of sulfur and phosphorus. Form strong covalent bonds. And I should add the versatility of carbon makes possible the great diversity of organic molecules. Each with particular properties that emerge from the unique arrangement of its mostly carbon skeleton and the chemical groups attached to that skeleton. Okay. So, that is it for concept 4.3. We have finished chapter 4. Just to go over real quick, we went over 4.1. Organic chemistry is key to the origin of life. 4.2. Carbon atoms can form diverse molecules by bonding to 4 other atoms. And concept 4.3. A few chemical groups are key to molecular function. Okay? So, next video we'll be going over the structure and function of large biological molecules, chapter 5. So, I wish you guys the best. Wish you luck on your studies and everything. And I'll see you guys next time. Bye.